So welcome to the weekly colloquium at the School of Astrophysics. I see some new faces. This is going to be part of your weekly schedule for the coming 1 or 2 years. So we are glad to have Dr. Anindya Ganguly from Inter-University Center for Astronomy and Astrophysics as our speaker today. Anindya did his undergrad from the Scottish Church College. We have some current student uh, accidentally joining an alumnus talk, which is nice. And then Anindya went to the Rajabajar Science College for his master's, and then to the Tata Institute of Fundamental Research, TIFR in Mumbai, where he worked with Professor Saurabh Chatterjee. So Saurabh Chatterjee happens to be our classmate. Dr. Shamu is classmate for both BSc and MSc, and SC ma'am and my classmate in the MSc. So
he will also come to give a talk
right,
for
and
the GR.
That's right. Saurabh will come next month and give a talk in our GR symposium. And he has previously given talks, lectures in 2016 GR school as well, GW school. So after his PhD, Anindya went to IUCA as a postdoctoral fellow, working with Dr. Anuprita More, who was also our speaker, as our students reminded me, in 2023 or 24.
23.
And so Anindya has done different things in his PhD and postdoc years, and he's going to talk today about about potential sources to be discovered in the new Rubin survey that's going to start very soon. It's one of the biggest projects in astronomy ever, and we are eager to hear about that from Anindya.
Thanks for the introduction. Yeah. So welcome everyone in today's talk. So the title is Discovering the Unlensed and Lensed Optical Transient in Rubin-LSST Simulations and Detection Methodology. So this work is done under the supervision of Anuprita More, and the collaborators are Surud More and Prajakta Man. Prajakta is currently a PhD for grad student in USA. She is still working there in LSST project. So I'll just give the outline of this talk. So first I'll talk about the telescope itself, which we are using is the Rubin-LSST. And then I'll talk about the transient, the things that we're going to use to detect the, to do our lensing simulations and all this thing. And then I will talk about why transients are important in the aspect of cosmology, and then how lensed optical transient can help, and then the simulations and the detection. So first I will start with Rubin-LSST. So Rubin-LSST is, as I told, that it is the one of the most biggest project in the optical astronomy. So it will run for 10 years from now on. So it has started its observation in the last October 2024, and it is in Chile. The mountain in a mountain, it's called Serra Pachon, and this is the image of the telescope, and this is here the camera is. So the camera of this Rubin-LSST is the biggest and biggest camera that have been used in optical astronomy. So several institutes from India are part of this Rubin-LSST project: IUCA, TIFR, NCRA, IIT Indore, IIA, and IISER Pune. So there are currently 27 PIs from these different institutes whom we are working on this Rubin-LSST data, and these are contribution from different fields. Like we are doing the lensing part, galaxy thing, and then there are people from cosmology, galaxies, and all these things. There are 108 junior associate currently in India who are working in Rubin-LSST. So as I told you, it has the biggest digital camera ever built for astronomy. So this is the camera, the animation of the camera. The size of the camera is 5.5 feet tall and 12 feet long. and compared to a digital camera, it's around some millimeter to. So the biggest thing, the science for this thing is, if you have such a big camera, so you can image a very big portion of the sky very quickly. So your field of view is huge. So for this camera, the field of view is 10 degree. So 10 degree means you can fit 40 moons inside one observation of this camera. So I'll show you. So this is one image of the camera for the full ACDs, all the ACDs if they are working, and this is the size of the moon in the sky. So if you want to detect anything that is faint and you don't know the position correctly, so you have to use Rubin-LSST. And the resolution of this camera is 3.2 gigapixel compared to a 2 to 50 megapixel that regular cameras are. So now this is the RADEC map of our sky. And as Rubin is situated in the southern part of our is the southern part, so it will observe the southern hemisphere. So these different colors are showing the different fields. So in our case, the most important things are the wide, fast, deep. So WFD means wide, fast, deep. So these are the regions that Rubin will observe with its camera, and this region will have more than 80% of time of the telescope time. So the other color region, these are for different specific purposes, and these will have different amount. This not that many visit compared to the blue region. So, and here now you can see that there are several small yellow patches. There are seven of these. These are, one is Chandra deep. So this is the Chandra deep, and then there is a 47. This is a globular cluster. So these different yellow patches are the preliminary observation that happened in last October to December of 2024. It is kind of a trailer of the Rubin-LSST. And for this, the camera size is used is not the full camera. So this, if this is the field of view of the LSST full camera, the yellow one region, this only use this small white patch. This is the LSST ComCam field of view. This is much smaller compared to the LSST real field of view. So now how LSST is going to observe the sky. So here you can see, so these are the different field of views. As you can see in the previous, this one pointing of this telescope, that one sky, it will see in this patch, and then it will go for seeing the sky for multiple times in the same visit. So this is one tiling of the Rubin-LSST is happening around the sky. So it will see now, yeah. So now you see, so it is coming back in the same region. So it is coming back to see the same region. This will happen till 10 years from now on. It will see the multiple same sky position again and again. So it will go on doing the same thing.
So how it will come back after what, 3 days or after how
for
much?
a wide field survey, wide field deep that we are talking about, a sky patch will be observed within 3 days, 3 to 4 days. It will observe the same sky. So around 10 years, you will have for a particular field 800 visit.
And what are the limiting magnitude?
Yes, so I'll come. So the limiting magnitude, it depends on the different, say, 7 filters that it has. So for a single exposure, so what I mean single exposure is this one patch, once, just see once. So these magnitude limits are 24, 23, 25, depending on the filters. But if you acquire all these images for 10 years or long time, so then the magnitude will go up to 27. So it will go deep. But okay, I will come back. So in this way, so the moment you see, it just quadrate the image, it's an animation, but it will just increase the depth, which I was talking about. It will go much deeper.
So it's a half sky survey down to 27 magnitude, and a
If you
3-day variability survey up to 24.
23, 24 magnitude. Yes. depending on how fast your transient or variability is. So these are the DP1 data fields. These are the different 6 filters. This U, G, R, I, Z, and Z. These are the wavelength and the coverage, the full width half maximum. So you can see that the DP1 there is not that many images. There are 4, 5, 10 because it's a small part that I've observed. And even using this, so we have a very good sky image of this thing. But you can see that there are all 189 CCDs. Only these 9 CCDs have been used for the DP1 data. So it's only have a field of view of 40 R, 40 cross 40 R. And after doing only these 9 CCDs, you will get this amount of detailed image of the sky. So this is one image you probably have seen in the Rubin fast light. So now, as I was talking about the variability and the transient. So any transient or variability means something, some object in the sky which is changing its brightness or magnitude with time. So that we call transient. So it can be repeating like it can be pulsating or variable that can repeat its light curve, or it can be a one-time thing, that transient. It goes on, explode, you have a very high magnitude and you don't have this. So how LSST will going to detect this thing? So here you can see, so this is called a static sky of LSST. So how LSST will see the static sky? So it will add different stacking images for different nights or observations. And then you will see that all the static object in the sky, it will remain in those different images, observation images. So what you can do, if anything changes in your recent image, so this changes, so you can subtract all the static thing in your images from different previous observations. And you will see that only the object which is changing its magnitude in some time, it will appear. So this is called difference imaging methods. It seems to be very easy, but it's very hard to do because each night your atmosphere between your observing thing and your atmosphere, the Earth atmosphere is changing. So there is some disturbance is happening in the atmosphere. So you have to correct for all the nights disturbance in the atmosphere. It is called seeing in astronomy. So yeah, you have to take care of all these things.
But what should be the delta M to detect?
The delta?
Minimum delta M, magnitude change can be detected.
Okay, so the way we are doing it, that if you subtract 2 images, then you have to detect these things if it is greater than the 5 sigma limit. So
The change you mean?
change. So if you add multiple images, so the thing is your static template, it depends on how good your static template is. So the way it is done is you take your best images from your previous observation. Okay, then you stack all these images and then subtract it from your current image. You match your PSF modeling and all these things, and then if it is greater than the 5 sigma limit of the current observation,
So what's the average magnitude uncertainty
in
any image? On approximately what kind of magnitude uncertainty do you expect? Like 0.1 magnitude, 0.01 magnitude, point something?
Okay, so this depends on the seeing and
but in the given
millimagnitude range.
Millimagnitude. So then something has to be like 10 millimagnitude apart. That's good.
So now I will talk about these different type of transient, which are I will talk about most of the famous transient that can be used in different purposes. So one of them is a supernova, and the most famous type of 2 supernovas are the type 1a supernova and type 2. So the classification is done based on a different thing, that if you see a hydrogen signature, if there is a hydrogen present in the object, hydrogen line present in the object, then you call it a type 2 supernova, and if it is not present, then you call it a type 1 supernova. So this is in the top panel, this is the image of type 2 supernova 1987. So here you can see that the Hubble telescope, and this is the time when it is observed. So here you can see this ring is so the formation of type 2 supernova happens is if it is core collapse and this explosion is happening, the star throws away its material and you will see the explosion. So here you can see that this star is throwing away its outer envelope and from the core region, and with time the core is also exploding and it is touching this region. So there are having due to the shocks and all these things. And in the lower panel, you are seeing this type 1A supernova. So this is the supernova that the formation is not happening due to a stellar collapse or explosion. This is happening because of a white dwarf is accreting material from another main sequence star or a giant star. And this can also happen in another case if two white dwarf is merging. So then this can also generate a type 1 supernova. And the other type of transient that we are interested in kilonova. So I'll tell you why these two I have chosen, that supernova and kilonova, they have some specific use. So, but for kilonova, we have only detected one kilonova with a GW counterpart. So this is GW 1787, and you can see again, in this time, this is becoming bright in a HST image, and then it is going dim and dim. So for this reason, these are called transient. It just increases its brightness and it goes away. So here the kilonova is, and this is the hosting galaxy. So I'll talk about a little bit more about this transient kilonova. So here is the animation of how these things happen. So two neutron stars. So these are the last product of massive stars. So after the death of massive stars, this can create black hole or neutron star. So here they have created two neutron stars and they are going around each other. So in this way, just before you can see these are emitting gravitational wave, and after merging, these have emitted electromagnetic wave. So these kind of thing can be modeled with very simple kind of animation kind of thing. So these are the three different type of materials that ejected when two neutron star merges, and they have different type of material because they have different opacities. So this blue one is the low opacity material, and then the purple one is the some medium opacity material, and red one is the very high opacity material. So if you remember, so all these lanthanides in our periodic table, these are generated from this red ejector. These have been postulated or have seen that some of the materials is really present in GW 1707. So from there, people are saying that this might be a progenitor of these kind of materials.
So, Anindya, just the schematic that you are showing.
Yes.
So does it mean that there's, the red, blue and purple, the size, the area that they are covering in the neutron star, is that related to the amount of radiation or amount of ejecta coming from those three kinds of, did I make sense what I said? So you said that purple, blue and red have different kinds of opacities. Is it correct or wrong to assume that when the ejector comes, a large fraction of it is from the material which is of the red kind, and then much less of the purple kind? Is this schematic
exactly
related to that? Or?
Yes, I'll just show you that how these different amounts. You are asking the different amounts. So here, so these are the different opacities and the masses that have been ejected for GW 1707 that we know of, the kilonova. So these are the fit models. So if you
then it's not to the scale, right? Because the total mass is less.
The total mass?
Total mass is less.
No, this total mass is the ejecta mass. And then there is also a black hole formed. Because, this total mass is the ejecta mass. So all the mass that you will see in the electromagnetic part. So what is
the volume?
So what is happening? So what is happening? So you can see that the blue ejecta have a little lower mass compared to the purple ejecta, and the velocities are also different. Okay, so it's have a very high velocity. So it's just fast. The blue part is fast, purple is moderate, and then the red is the slow. I'll show you that what will happen if these values. Huh? No, sorry, the red.
Then the density.
The key.
Well, K is
Okay, is the opacity. Opacity of different ejecta.
Kappa.
Kappa.
gamma per centimeter square is inverse. Inverse of mass per area. Inverse of that. Kappa.
So blue is the low opacity material, and the red is the high. So
Yeah, I mean, yes, the capacities still are quite different, like 0.5, 3 and 10. But the masses and the velocities, there must be some errors on this estimate.
yes, there are errors.
So are they still consistently different when errors are considered, or? I mean, is it 0.1 plus minus 0.1, or is it 0.1 plus minus 0.001? So then I can make a difference that red and purple have different velocities, because one is 0.1 C, one is 0.15 C.
Yeah, so
Yes, I know the errors. it's
so
not the same.
these estimated are done in a Bayesian way. So the correct error I don't remember, but I can.
10%, 5%, what is the level, do you remember? No?
The level I don't remember the value,
that's
but I
something
have
else.
done empirical check that what happens if we don't consider these three kind of ejecta.
Okay.
So this is the fit. This is the more or less the fit of for different these values, and these are the observations. So what will happen if you increase the blue ejecta value? If you increase the mass in the blue ejecta, so the blue ejecta now is dominating. So what happens is you can see this dashed line. These are the new line with the new ejecta value. So it just goes up in the initial part of the emission. So blue ejecta is actually dominating in the initial part. And so what I did is I make it around 0.1 solar mass. So it's very high. So you just see that this part is dominating due to the blue ejecta. But in the later part, this is not changing the light curve that much. So this is the light curve. So this x-axis is the MJT and y-axis is the apparent
And
magnitude.
those are all different bands, right?
Different bands. Yeah, GRI.
Are they same?
Huh?
Different bands, they are same, or there is also different between different bands?
No,
The
the
light curve?
The changes.
the nature of the light curve. The nature is same because it's the same.
Or any time lag or anything? Means, do I get any more information considering individual bands, or they give more or less similar?
You will see the shift of the peak in different band because the reason is at a different band if you are using this
Opacity will be different then.
this G band, so then you will see the effect of the later the red ejecta in that part. So you will see little bit longer in the this after blue region. So I'll show you that. So if you just increase the purple ejecta mass, so in this the mid region it just depart from the exact peak. So this mid region dominated. And the interesting thing happens is here. So when you increase the red ejecta part, you will get a very long afterglow. So for all the infrared instruments, they are looking for this long afterglow thing. If the red ejecta mass is very low, then it will just drop. But there is also a effect of velocity. Here I am showing the if you increase the purple velocity and if you increase the red velocity, what will happen? So you can see that there is a little increase in the initial part, but in the later, in this part, you see that the drop is happening faster. So the reason is the envelope it is creating, the material is creating. If the velocity is very high, so it will just disperse or diffuse very quickly. So that's why your brightness will drop if you have a very high value ejector. So in this way, you can also, depending on how fast the curve is falling and increasing or have a long tail, depends on the ejector of this material.
So what is this MOSFET gain model?
Oh, so MOSFET is the Modulo is a Python package to fit this Kilonova model. Not only Kilonova,
So this is
transient.
like an what is there a physical model?
Yeah, there are physical models for all different transient.
And you have developed it or?
No, I haven't.
It's
developed it.
available.
It's available. It's available.
Sorry.
Yeah.
So in this case, you are considering only these three properties. But you have the geometrical properties as well.
Yes.
So they will also change this thing.
Yes. So the geometry, the angle, and way you are seeing,
Correct.
it changes the thing.
Not only the way from where you are seeing, also the ejected angles. Those angles,
Yes.
they will be also.
They will have dependency, but current models from different groups that have been showing that it's not very highly dependent on the angles. So if you get almost similar kind of fit without using an angle and with the angle model, so we are currently not using a specific angle. You are not using in this part a specific angle. So it's just based on different physical properties. So now why we are interested in transient? So the one thing that you can study the transient, the different transient, their mechanism you can know in supernova, kilonova. But there is another thing in cosmology. There is a constant. It's called a Hubble constant. So it measures or sets the different physical scales of our universe. So what is Hubble constant? The Hubble constant at present day, the value of the Hubble constant in present day is has a debate. So you can see that from these two different measurement. So the blue one is the Cepheids. So what happens is Cepheids have a very Cepheids or the, as I told you, type 1 is supernova. These are called kind of standard candles. So they have a very well-known luminosity. So if you place a Cepheid nearby, the luminosity, the intrinsic luminosity of the Cepheid, and if you place it a very farther away, the intrinsic luminosity will be same. So from these information, the intrinsic luminosity, you can estimate that how far the Cepheid is. If you know the information of the host galaxy. The same thing is true for the type 1 supernova. You know the luminosity peak very well. And in this way, you can have an estimate of different distances in our universe. And from those distances, if you know the redshift at those distances, you can estimate the Hubble constant at your in present day using the Cepheids and type 1 supernova. And these values falls around 70. And then you have your early universe probe. So these are model dependent, the early universe probe. So you have a CMB measurement from different instrument, and you then fit your flat lambda CDM model, and from there you estimate the Hubble constant. So here you can see that around before the Planck estimates, these were almost in the similar, there was no problem. But after the Planck estimate, these were become very precise measurement from the early universe. And then it creates almost a 4 to 6 sigma tension. So it means these values is not matching within 4 to 6 sigma. And then there are multiple other also probe. This is the tip of the red giant branch estimates. These are also local universe estimates, but this falls somewhere in between. So the point is there is a problem in the estimate of the Hubble constant, and we are very concerned about this estimate Hubble constant because it sets everything in cosmology: the physical size, the time of the age of the universe, and all other things. So yes, this is a serious problem. You can see that how many publication is going on in this for Hubble constant to estimate the Hubble constant. So in this one side, this is your CMB sky. So this can be you can see there are small differences in the temperature, but it more or less a very uniform map. And from these CMB estimate, they have come out Hubble constant value 67.4 kilometer per second per megaparsec. So it means that at a 1 megaparsec distance, if you find a galaxy, it is moving, it is recessing from you at a 67.4 kilometer per second velocity. And then you have these local probes that I talk about, the Cepheid, the type 1 supernova, and these values are around 73.4. So there is almost a 4 to 6 sigma difference. So then there is cosmological community saying that is this a new physics or systematic? Systematic means we are doing are you doing any mistakes in our estimate of local universe probe or the early universe probe? So to test this, there are these three different probes. This is the early probe from CMB, local probes type 1X. And then there is another probe from strong lensing and time delay cosmography. So these strong lensing and time delay cosmography doesn't depend on this early probe and the local probe. So this is an independent probe. So how time delay cosmography works? So here you can see that there is another transient thing is going on. So here, this is a massive galaxy. Okay. And behind this massive galaxy, there is a blazar or AGN or any transient source. So if light is coming from this blazar and passing through this massive galaxy, now from gravity, this light will get bent. You can see this is the lensing galaxy. So here you can see that depending on the which part of this lensing, the galaxy potential the light is encountering, it will have a different path. So immediately you can see there is a different path length for the same light. So now if there is a transient event happens, so here you can see depending on the path length and also where the galaxy potential it is encountering the signal, depending on that potential which is also retarding the light, that will create a time delay of the same transient signal. You can see that when it reaches, there is a time delay. So from this time delay, you have an estimate of these distances. And from the distances, actual distances, you can have an estimate of the Hubble constant. So I'll go little bit detail on how we will do it. So this is again a schematic diagram of this same thing, the source and image and lens. So you can see that this is the source and there is a lensing galaxy. This is a massive lensing galaxy. And if there was no lens, then the light will come directly from the source to your Earth. Nothing will happen. If you have a lensing, so if any light going in this direction, it will just be bent and you will see the image here due to the gravitational effect. And these are the different angles. So you can create so all these things are very small angles. So if you see in the in numbers, these are within arc second. So these are very small angles. So you can have a relation between your source angle, the image plane angle, and your deflecting angle. So where this deflecting angle depends on the potential of your lensing galaxy, where it is passing through the galaxy. So you can see you can now have a potential, scalar potential, and you can map these deflecting angles using this potential. Now, how you will measure the time delays? So in the observation, you will have these kind of images. So this is a composite image you will see in the sky. I will show you some real images, but this is a simulated one. So what you will see, there are 4 different images of one background source. And this one is your lens galaxy in the middle. And these arcs are coming from your galaxy of the host, which is in background. So this is your observation, and you will now create a model to match your observation. So the 3 things goes in creating a lensing image model. So first is the lensed AGN light. So AGN means any transient. So if you have in the background any transient, it can create multiple images. As I showed you, it can create you multiple images for the massive galaxy. And then you have your galaxy where the AGN is present. It will also in the same way, it will also lens the galaxy. So you'll see the galaxy arc here as an image. And then you have the lens galaxy light, which is not lens, you just see your foreground galaxy. So to estimate this part, the lensed AGN light, you have the AGN position in the source plane. Now you see that this is a free parameter. So you don't know exactly where your source is. You only have this kind of observation. So what you will do, you have your source parameter as a free parameter. Then you have your lens mass model. You know the lensing galaxy. You have your lens mass model. So you add these two things and you do the lensing. You will see these kind of four images. Now you remove now you position your source in a way to create an image that matches with the observation. So in this way, you fixed your source position, you can estimate your mass model parameters and all this thing. And then if you want to also include the host light, you will take a AGN host model and do the same thing. And the lens galaxy light is not lens, so it will be just present there. So in this way, you have a control on the beta value. This is the source position value, and the phi, which is the lens mass model. So if you have estimated this thing, then you estimated the this is called Fermat potential. You estimated the Fermat potential for each position in the image plane. And if you know the Fermat potential now, as I showed you, there will be two different. The transient will come at two different times. So this will be your delta T AB, and from this you can estimate the actual length, and from this you can estimate the Hubble constant. So it is little bit model dependent, but you do not depend on the type 1a supernova or any other things. Now, if in case your transient is a type 1a supernova, then you also know the distances very well. So that is a extra benefit, but it's not needed. So to do all these things, we mainly use the supernova and kilonovae because these are the bright this supernova is very bright, and the kilonova you might have a GW counterpart if you have a GW trigger from your LIGO Virgo observations. So now this is a real image of a strongly lensed supernova in the HST image. So you can see that here, these are the four images. This is a real image of strongly lensed supernova. And then in the cake, there is also four images. So these are the very rare objects. There is only 6 of them where you can see these kind of clear images of a strongly lensed supernova. Now, what will happen in LSST? So there are simulations and studies going on that how many of these lens transient, so at least supernova, strongly lensed supernova can be detected. So there are almost 10 to 100 strongly lensed supernova that can be detected in LSST. As you see that LSST covers the sky very rapidly and with very depth. So it will be very easy for LSST to find these kind of sources. But the problem will be there will be too many alerts and all these false positive. There will be millions of transient events that will come to us, and we have to tell them that this is a false positive or this is a real source. And if you detect 10 of strongly lensed type 1 supernova, then your Hubble constant can be constant within 1.5%, which is now the standard limit from CMB and all the other things. But the thing is, the lens kilonova sector in the Rubin-LSST is not explored well. And one interesting benefit that I told you, that lens kilonova or any kind of kilonova, they have a chance to have a GW counterpart from LIGO Virgo. So if we detect a lens kilonova, that will be a very valuable target to all these things, because we will have a information constant from the GW. So that's why I mainly work in the lens kilonova part.
Sorry,
Yes.
For supernova case, you might have the redshift of the supernova as well.
Yes.
But for kilonova, do you also get that, or?
If you observe the host galaxy, if you have a spectroscopic measurement of the host galaxy, the kilonova which is in the host galaxy,
That is the background of the foreground.
But for the luminosity distance, GW estimates, you can have a this estimates of the background source. So you can see that there are here you can see the arc of the host galaxy. So from there, you can do a spectroscopic measurement of the host galaxy. If you and then if you have a GW counterpart, that will give you a luminosity distance of that source. So yeah, you need the redshifts of the background and the foreground. So what we do is we start with the simulations that at all how many lanes kilonova or at least kilonova will be detected in the LSST. So we start with a binary neutron star merger rate distribution. So here you can see that this is the redshift and this is the number of merger rate that might happen. And different tau and alpha is tau is that you generated two neutron star, and now after generation of these two neutron star, how much time it will take to merge, at least minimum time. So if you take, we have taken three sets of time, so 10 million year to 1 gigayear. So 10 million year means the moment you have created your neutron star, it's merging very rapidly compared to the 1 gigayear. So it will take at least 1 gigayear to merge for a different. And these alpha values, this minus 1.5, this all this minus. So minus 1.5 is this alpha value is saying that it favors the rapidly merging neutron star more compared to the 0.5 value. So you can see.
So yeah, how do you are writing it here, but how do you make this distribution, like construct this distribution function as a function of redshift?
Yeah, so you have the star formation rate density.
Okay.
And then you convert it with this delay time distribution, which is a power law.
Yeah, but when you do the star formation rate density, then that's just star formation.
Star
then
formation.
Here you're thinking about like BNS mergers.
BNS
right?
merger.
So
So
then,
you
from the global star formation rate density, how do you infer the BNS? Because not everything, this is just global star formation. A lot of it will be like, just we will not end up in binary mergers.
so that's the reason we are using this delay time, this binary evolution time. So it's coming from the binary physics of neutron stars. So how much common envelope and all these things, all the binary physics and the GW in spiral time, all these things, these are encoded in this delay time distribution, and that is a power law. So this
and the delay time distribution, that thing is being generated from this Belinsky type model, or how do they do that? I mean, because there are many ways for this, as you said, common envelope and all that.
So they are mainly doing that you create your binaries in the simulations and you see what is the power law dependency on your semi-major axis in different part of the process. If you are doing a mass transfer, what is the dependency on semi-major axis? How fast it is shrinking? If you are doing a common envelope, then how fast? All these things are power laws.
So would I be right in assuming that this is a phenomenological model?
Yeah. It's a completely phenomenological model. All the models are. So it's I think it is not possible to constrain these parameters till Einstein telescope. You need much more than 50 neutron star binary neutron star merger to constrain this.
But that model, whatever you are talking about, that is the after formation of binary neutron star, how they are going to evolve. But even before that, there is
Then how many
uncertainty
neutron stars
many
will
binary
form?
neutron
I think
star
that
will
was my
form.
question. That
How many binary neutron star will form?
I think
That
that was my
has a
question.
model dependent. Somehow that has been modeled here. I don't know. So that model is there.
Yeah, that was my point, that from the global star formation, because Menow and Dickinson, this is global star formation rate. So from that, how do you infer that how many neutron star binaries are likely? So that distribution, there must be some more modeling involved.
Yeah.
I don't know if it's stellar population, I don't know how there, maybe something is involved.
Okay. Yeah, I'll check that. I'm not very currently sure that part of modeling. But we start with these models, and these are the most available and detailed model to take a binary neutron star merger rate distribution. And what we do is we randomly draw our kilonova for this entire redshift range following these distributions. So all our initial kilonovas are from these distributions. And then what we do is we use the MOSFET model, and for each kilonova, we attach a light curve. So we give this M ejecta, these 3 ejecta values, velocity values, and we create a light curve model for that particular kilonova at that particular redshift. So here is an example of the light curve model in all the LSST bands. And you can see that this is the time and this is the magnitude. So time means from the explosion of the binary neutron star. And you can see these all the horizontal lines. These are the LSST single exposure limit. So means you take one image of LSST, you go this amount of depth. So this for Y band it's around 22, it's around 23.5 for Z band, and these are the things. So, and then what we do is we take this kilonova and randomly distribute that kilonova in your LSST field. Okay. And then we try to observe that kilonova. That if it is possible to observe in LSST fields. So you see that these black dots, these are the time when an LSST mock observation will happen for particularly for this kilonova. So it generated a mock observation to say that. So you can see now this point is just above this range, and this point is just around this range. So from these 1 or 2 points, we have to tell that is it a kilonova transient or a supernova transient or these things. So this is a way to show that how difficult it will be to classify this kilonova, classify this transient event, and this will happen also for supernova, similar kind of.
The time scale is less than 3 days.
Exactly. So that is another problem. So you can't stack this thing, and you can't even if you see.
Then will you be able to observe the kilonova at all if it is less than 3 days?
Okay,
so chances are missing it will be much more.
Yeah. So I didn't talk about at all I always talk about the wide field, wide fast deep survey. There is one survey mode. This is called the target opportunity observation. So this is called TOO. So the moment you have a GW trigger from a kilonova, LSST will go on that patch and it will observe that patch if you give 100 square degree with a much more cadence and go in a deep. I'll show you some depth limit for particularly TO observation. But yes, you are right. You have to be in a serendipitous way to discover a kilonova. It will be very difficult because you will not have a 3-day. But anyway, so we have simulated for all of these different merger rate, and these are the numbers for at least bright kilonova that have a peak magnitude higher than the single exposure limit of the LSST. So these are around 10 to 100 kilonovas per year that will be bright in the LSST. It will get observed or not, then we have to check it. But these amount of kilonova, if we observe them properly, we can detect.
But also you have the distance limit.
Yeah, so distance limit is already there because we are drawing it from the redshift distribution.
No, even if the kilonova has a particular luminosity, I cannot observe it for some any further distribution. Up to some redshift, I will be able to observe it with my limiting.
Okay, yes. That is actually okay. I understand. So these different 0.16, 0.15, 0.5 values you are seeing, these are those limiting redshift values.
These are those
limiting redshift. So that actually sets your how bright the kilonova will be. Most of the kilonovas that we simulated are below the LSST limit. So you can't observe most of them. So you can see that we have some 10 to the power 5 kilonovas intrinsically, and we end up with 10, 80, 30 of kilonova. Those which are very near to us, within 0.1 redshift. So now there's another thing that how to classify these different transits. If you just observe them in the sky, what will be some quick way to classify these transients? So what we have done here is these are the 4 different redshift bins. Okay, and for the time being, you just focus on the gray region, gray light curve, and the blue light curve. So these blue light curves are for type 1A supernova, and the gray light curves are from the different kilonovas in different redshift. And the red line, this is the bright kilonova, which will observe in the LSST. They have the peak magnitude higher than the LSST limit. So here you can see that at a redshift greater than 0.3, there is no bright kilonova. So this y-axis is your color evolution. So what we have seen that the color evolution for kilonovas is very fast compared to the type 1a supernova. So if you are in the low redshift regime, you will see that kilonovas are evolving in color very fast compared to the type 1a supernova. So if you have some photometric data point for a particular kilonova, and then if you want to compare it with the type 1a supernova, the evolution of color will be very fast in the kilonova. So we have also added some other transient of supernova of different types and TDs. So we have seen that the kilonovas have a very fast reddening or color evolution, that is very fast compared to the other type 1a supernova. But if you go to the higher redshift, these difference get decreased because of the redshifted kilonova, redshifted supernova and all these things. So now I will come finally to the last part of the how we do our lensing simulations. So this we start with a lens galaxy population that we have taken from HSC PDRC data. So that will be our foreground massive galaxies where the masses are greater than 5 into 10 to the power 10, and we have taken redshift up to 0.5, and the velocities are 120 km/s, because there is no point to take beyond that, because our kilonovas and all these things beyond this value will not be bright. So we start with following the Murray 2022 formalism, and we have now 500,000 real galaxy. And for each of these candidate lens, we draw a kilonova from the merger rate distribution. So our kilonova is coming from that merger rate distribution. Then we place that kilonova in the back of these massive galaxies, and we do the lensing simulations, the lensing formalism, the part. And then we only take lens source pair which have a Einstein radius greater than 0.4 RC. This sets the limit from the LSST seeing. So LSST seeing is not going to deeper than the 0.4 RC. So if you have an object that have an Einstein radius less than 0.4, you will not be able to see in the LSST. And we boost our sample because anyway the lensing will be very few in reality, but we want to do a statistics from this sample, so we just boosted the sample to get a reasonable number of lens source pair. And
if you don't boost it, what will be the number?
The number will be very few. Like there is only 6 strongly lensed supernova has been detected. So we don't go on that.
But if I don't boost, this number will be
few. Because we don't go in that limit, because that will not the statistics, we can't do the statistics with them. So here is the distribution of the lensing galaxies, and these are the source kilonova that with a redshift width, and these are the numbers. So these are the foreground galaxies, and in the back these are the kilonovas. And here is a sample example image of how this imaging of different things happen. So now after this lensing, as you see that the light is getting distributed. So in some cases, if the object is perfectly aligned within our line of sight and all these things happen. So in some cases, one image can magnify because of the redistributions of the photons. Because we are not losing any photon, but the photons are getting redistributed in your image plane. So what will happen in a different line of sight, you will see the fainter image. In a different line of sight, you will see a brighter. So we can use this property to boost the magnitude of the kilonova. So we look for this kind of, particularly this kind of samples where the high magnification is happening. So these are also very rare. So here you can see this x-axis is the source redshift, that is the kilonova redshift, and y-axis is this magnification value. So this 10, 25, 50, this amount of magnification can happen. We just multiply it with the flux. And here you can see these this orange circle, these are for double images. If there is a image, two image formed from a single source, we call it a double. If there are four images formed, we call it a quad. So this happens due to the orientation of the lens and source. So if we look for these kind of sources where the high magnification is very high, then what we can do is, it has been shown that in a high magnification sample, these images are very close to each other. So for two images, you can just add up your magnification and you will get further highly magnified images. So this only happens in case of quads. You can see that orange are quad. So quad two image will not be magnified, but the other two image that will be highly magnified.
So what is the fraction of this 30,000 lens galaxy will
Quad.
say 20 mu of 25 or above?
So there are so here mu we have added around 16 to 20 of them. They have highly magnified in quads.
Out of this 3 lakh, 16 to 20.
20 have very high. And the other number is the ratio of doubles to quads. So this happens mostly for quads. And now the doubles to quad ratio is 1:4 or 1:3. So doubles are much more in numbers. Quads are much less. And the highly magnified quads are also. So what we do is we take one sample of this and then we create a light curve. We attach a highly magnified candidate and attach a light curve of GW17087, which is at a redshift of 0.96. So if there is a kilonova at redshift of 0.96, we will not be able to observe it in the LSST. If there is a lensing, there is a possibility to observe. So what you are seeing, these are the different filters of LSST. And this solid line, this is the intrinsic magnitude. So you see that the intrinsic magnitude is very low, it's around 30, because it is a very high redshift image. But you see for the second and the third image, this magnification is so high, it just pushes the light curve in around the observable limit of the LSST. So the other thing is the time delays of these two things is also very low. But so again, if the time delay is very low, it makes harder to do a Hubble constant estimate. But that's a different thing.
That's the thing, no?
Yeah.
If you are seeing a quad image, that will be very centered to the lens galaxy, and your time delay will be very small.
It will
So and that will be difficult to
that
measure.
will be difficult to measure.
And if you have a
Of
axis image, that will have more time delay,
More time.
but it will be less mu. Mu will be very
So
less.
yes, if you are using a particularly a kilonova, this will be difficult because the highly magnified candidates are only from this kind of time delay, as you pointed out. But in case of supernova, if you have a quad, supernovas are bright, you don't have this problem. So if you have a quad, you 4 image, so you have a very good constraint on the lens properties, on the source properties. So then you can make a very good estimate of the time delay using a strongly lensed supernova. So this way that we can probably observe some of these lens kilonova if we have a GW counterpart. So here you can see the 30-second limit of the LSST is very high, but there is a 120 and 180-second limit. So this is the exposure time in TO observation, which is a dedicated. You have a GW trigger of kilonova, and you are looking in that region to detect a kilonova, and then if it is a lens kilonova or not a lens kilonova. So the thing we do is we create these kind of samples of kilonovas, and we give it to different groups which are doing the classification of these kilonovas. They mix it with other transient and they create. So you see that these kind of things are valuable targets. So we do not want to miss any of them. So that's why even it's a rare thing to do, but we still do this kind of would still look for this kind of transient. So the some of the future work is I haven't talked about how to simulate this in image. So this is the next part of this project, that we create a lens Kilonovae image. This is all the analysis is done in the LSST light curve part, but we have to do it in the image part also. And then there is another thing that we are using HSC galaxies, but there is already ILSST observation happened DP1. There are some galaxy bliss. We are going to use those galaxy bliss and then apply some difference image to detect these kind of sources. So yeah, these are the things.
Okay, questions, comments, thoughts, enhances? Yes, sorry.
Yeah. So could you please go back to the slide where we were fitting the light curves? Getting the different kappa, velocity, mass.
Yeah.
So you can see that you are fitting these light curves and getting those parameter values.
So-
But also,
I haven't done the fitting. Yeah,
but one thing is that if you increase the mass, you are seeing some rise in the light curves. And if you increase the velocity, you see some dip. So if we combine these two, there can be some kind of degeneracy. Do you get that kind of degeneracy? Like increasing the mass, it is going up, and again increasing the velocities, again coming down.
Yeah,
like
so-
these kind of things.
so the fit is done in a way that these are all considered these different, all these properties are considered as a free parameter. And then you have all the data and you create different models of Kilonovae. And for all different bands, you try to fit it in one go, in a Bayesian. So these are all constant in at a single time. So you can change it, you can have a better fit, but not you will not get all the fits, good fit in all the three parts. So the point is that you might have a blue ejector. If you increase, you are getting a good fit in the blue part, but you have to also take care of the red part. Everything has to. So the reason we have taken this MOSFET model, because they have done it for the first time for all three ejector. Because people usually do it for two ejector model, or so they have homogeneously did it for three ejector in a one fit.
Okay, other questions, Abhijit?
I have two questions. First is, what is the normal time delay between receiving two signals from transient by lensing?
So it depends on your lensing potential. So it can be go up to from hour for a highly magnified ones. These are going to some hours, and for a quad for a double image which are not perfectly aligned, that can be happen to days to months. All this we have different type of distribution for time delays. This depends on how the lensing is aligned. For very highly magnified quad images, the time delays are usually small, short.
Okay, did we calculate any Hubble constant using this method?
From my work, no, we haven't calculated the Hubble constant yet. But people have done it for 6 different strongly lensed supernova, and they are getting the values. So there's a project going on using the quasars, the time delay estimation from the quasars. So previously they were getting a values around 70, which matches with the late time probes, and later they are now doing a better lensing models, and they have increased their samples. So it is now coming the latest release